My name is Mike Strassmaier. I work at Intel in the data center group as a software architect, and I'm based out of Portland, Oregon. So during this talk, I'll talk a little bit about the Intel Optane DC persistent memory. I'll give an overview of the performance and the product itself. I'll talk about the challenges and importance of replication performance. And this will be kind of an example of talking about replication to kind of demonstrate how this new product really fills a gap in the storage, the persistence in the storage area. And talk about data replication, how we do it traditionally, and then what we can bring with the persistent memory using PMDK and the librpmem library. I'll talk a little bit about the PMDK API support, and then some performance considerations when using the persistence memory for replication. So many people have probably seen this triangle in various presentations, and what I really wanted to highlight here is there's really two main Optane products. We have the Optane DC persistent memory that was recently released that sits a little bit higher up on the pyramid than our Optane DC solid state drives. They're very closely related products. They use the same technology within the drives. The form factors are different, where the Optane DC persistent memory sits on the DIMM bus and sits with the DDR4 memory. And the performance of the Optane DC persistence memory is very close to DRAM, near DRAM levels. And the added benefit that you have with the DC persistent memory is the persistence. And as you look at the performance and the persistence, you can take a lot of capabilities that traditionally we performed in the SSD level, and we can move that up to a higher level into the DC persistent memory. And replication is one of those cases, and that's why I wanted to bring that in as an example of where we can bring a lot more value into the technology with the typical functions that we would perform on an SSD. So I have a glossary of terms here. So we actually had a brief discussion just prior to the presentation on, the different products. So we have Optane SSD, we have Optane DC persistent memory. They're two different products. And then we have standard 3D NAND SSD, and I'm going to show some of the performance data from that. And then of course, we have DRAM and the other standard products, and I'll kind of show how these fit into the performance hierarchy. So I'm happy to share some data that we, from our benchmark testing with Intel, taking a look at the latency and the bandwidth on the DC persistent memory. And if you look at the y-axis on here, this is the read latency in milliseconds. And you can see where on the bottom line we have the Optane DC persistent memory, and the read I/O latency is very close to DRAM, just slightly higher than DRAM, but it is actually much quicker, or the latency is much lower than the Intel Optane drives. And then on the very top we have the Intel NVMe 3D NAND drives. So this really kind of demonstrates where our performance sits in the hierarchy. If you look at the x-axis on the bottom, this is the actual bandwidth in gigabytes per second. And if you scale this graph from the Optane DC persistent memory up to the NVMe SSD, we're at about 1,000x faster. So the other thing I'd like to highlight is the DIMMs are normally placed in a system in pairs. So you may have 2, you may have 4 DIMMs on the board. They work together with the DRAM. The data on this chart is actually a single DIMM. So as you add more DIMMs, of course, you have additional bandwidth. Now I'm going to add a little bit more data to this chart. And what this highlights is that with these additional transactions, that different latencies are experienced with different block transfers, or the granularity. So on the left here, you can see at the 64-byte level, read-writes are much slower than if you move to the right, where we have 256 256 gig block sectors. When you get 4K and higher, it's generally much faster performance. And I have a chart that really shows or demonstrates the performance differences with the granularity of these block sizes. Also, I would like to highlight that if you look at the overall bandwidth, the DC persistent memory is about 3.7x greater than the NVMe SSD. So the bandwidth is much greater on the persistent memory, DC persistent memory. So, taking a look at the performance, the wattage. The power settings or the power performance optimization set really in watts, and we can run all the way from 12 to 18 watts with a 1/4 of a watt granularity. The chart down below shows the bandwidth that you can expect with a granularity of 256 byte blocks, and then at the bottom you can see where you're not able to use all of the lanes, that it drops down at 64 bytes. So these are the read-write and then read-write grouped together bandwidth rates for the persistent memory. So of course higher performance gives, or higher power settings give higher performance on the memory product.
How do you set the power?
I believe it's set internally. It can throttle itself back if the heat gets to be excessive. And I believe on boot up there's another setting that you can do to adjust the performance.
The BIOS.
The BIOS setting, yeah. Now, this chart is just another visual representation of the NAND versus Optane SSD versus the persistent memory application latencies. And a couple key takeaways here. So you can see where the read performance is much better, so that reduces the latency. And your shared file system or your OS driver is really non-existent on the DC persistent memory. So remember, this memory sits directly on the bus on the motherboard. So you don't have this remote attachment where it requires the software that is managing your file system, the OS drivers, and so on. So this is one of the key aspects of the product that really brings a much faster performance. And then the center block is really the Optane SSD. You can see the improvements between the NAND drives and the Optane SSD with the block in the center. Now, I'd like to kind of change gears a little bit and talk about one of the use cases that we've looked at where you can get significant value out of the DC persistent memory. And this is in the area of replication. So traditionally, we use block devices to run our replication, and latency is a key factor that we're always trying to reduce with replication. So the real key questions that you have is, can the data replication tool keep up with your transaction log generation or not? So speed is always of the essence with replication. And then what is the time period that your data has been out of sequence while you're going through your replication? And the real key thing is you want to be near real time. With resource consumption, this is another consideration. You don't want to consume a lot of your valuable CPU resources in running your replication for your solution. You also need to take a look at what network resources are going to be used, try to minimize that, and then you have to look at your network and memory usage also. So with traditional data replication, it's I/O bound usually, and it's usually implemented using the kernel driver, I/O. You have management applications, software at the software level that really move the data back and forth. And I have some diagrams that really kind of show at a high level what you're doing at a high with replication, both with the traditional method and then the method that I'm going to talk about on persistent memory. So with your data replication API, you have layers, usually logical block devices like SSD or HDD, hard disk drives, moving data from your initiator nodes to your target nodes. And normally that there's some type of read, write, that's a lengthy transaction, and then some type of acknowledgement that comes back to your initiator node. And this actually can consume quite a bit of resources, not only from your network, but again from your CPU and so on. So we ran some test cases on IO-bound data replication within our environment in Intel. I have the specs here. We're using a 4096 block size, which is fairly standard. Our file size was 10 gig, using a standard file system. And what we found is we measured each logical step or block during the replication process. And we have your local read-write on your SSD or your hard drive. And then you have your DRBD transaction times. You have your RDMA when the data is packaged, moved over to the adjacent nodes. And then you really have to take the time to rewrite that to the target node, and the test case that we had, it was over 60 milliseconds. Microseconds, yeah. So,
What protocol did you use for the RDMA transfer?
this was, I don't recall, it was done by our team in Poland, so do you remember?
This is the Linbit ships this version of DRBD that will replicate over RDMA.
It has its own protocol.
And I believe it has its own protocol. I'm not sure if it's built on top of the fabric or not. I think it is, but
Yeah.
Okay.
you might go directly to the first.
Okay, we ran the same test using replication over RDMA and persistent memory using the PMDK RPMEN library. And really the RDMA is a low latency high-speed network interface that controls the movement from the initiator to the target nodes. And it's really a one-side operation when you're doing this over using PMDK. So the direct memory access is really moving the data from your initiator node to the target node without involving the CPU. As you can see in the diagram here, there's still an interface between the CPU and the RDMA capable NICs, but really the data transfer is going from the initiator DRAM on the left, or Optane DC persistent memory on the left, to the one on the right. So once the persistent memory is accessible through the remote connection, we can expect significantly lower bandwidth because it's simply more efficient not to involve the CPU, and just when there's a change detected on the initiator node, just to automatically push that to the replication memory is much more efficient than traditional replication. So it's really a superior solution for a lot of the infrastructure as a service deployments. And this is really the test case that we use at Intel. Really, it's the same size files. We're using the same 4K blocks. We were using two 256 gig Intel Optane persistent memory modules, 10 gig device stacks. And you can see the average latency by component. And again, this is on a 4K sequential write. You can see where we have the write to the persistent memory. We have the DMA transfer, the RDMA transaction, and then there's an acknowledgement that happens at the end. So in the previous example, we were at roughly 60.15 microseconds. Here we're at 6.76. So it's a much quicker replication strategy using replication on RPMEN. This is a better visual of really what's happening. So on the left, with your traditional data replication, you have multiple hops. You're going from your block storage device to CPU, then usually to your DRAM memory, then you go across your Ethernet, and then you can see on the target system where you're going back into the DRAM CPU, and then you're storing it off into your block storage device. With the data replication on the persistent memory, it's really one hop, or I guess you could say maybe it's two hops. So you do some processing on the CPU. Whenever there's a change made to the DC persistent memory, it's automatically replicated to the adjacent or to the target node. And I put the two bar graphs together on the bottom. And I broke this out by the network fabric, the workload that's happening on the network, the NVM media, and then also the software transaction times. And you can see how much quicker the performance is using data replication using RPMEM. So our PMDK version 1.6 implements both what we call a general purpose remote replication and the appliance replication method. The librpmem implements the synchronous replication of local writes to persistent memory on one or more systems. And I have a couple diagrams and flow charts that really kind of walk through what is happening in the background, really what's going on under the hood. So librpmem is a low-level library that allows other libraries to use its replication features. To take advantage of this, the persistent memory on the initiator and target nodes the application needs to make sure that these are persistent aware and that they're able to do this replication. So I have a small diagram on the bottom that really kind of shows where this work is being done at the live RPMEM and the live, really down in the object libraries rather than at the application level. Okay, so there's really two steps to replicating using the RPMEM method, and what you first have to do is you first establish a connection, and then the second step to the replication is really the process to monitor what's happening on the initiator's memory and doing the replication automatically is kind of a push system. So I have kind of a full flow chart here that walks through the steps that are happening in the background with the replication. So first there's a local pull configuration file that makes a write to the library object. And then that object maps the file and pushes that into the local memory file. After that, there's certain calls that are made to go out across the network to check on the endpoint of your target or your target nodes. And once that is done, it has listened for this request, and then it replies back, and then the data is moved over or memory mapped from the target from the initiator node back to the target with the actual memory or with the data. And then there's actually an acknowledgement that goes back up into the libmem object and then back into the to the user. So the real key here is that you have a full established connection, that the memory modules are persistent aware of each other, and that there's a constant listener going on for any changes that are happening. Once the initiator once the communication is established, then the replication process is triggered whenever there's a write or a change to the PMEM obs persist API. There's a call that's a call or a change that's made to the libmem object block. Okay. Once this is made, then there's a change or there's a push out to the local memory file, and then this is actually moved over to the target node. And then it triggers the replication, the data is transferred back over, and then there's an acknowledgement back up to the initial node that the replication has been successful. So there's some performance considerations that you have to take into account when using the RPMEM RDMA replication. So in our test, the large block sizes demonstrated really good performance. So we were using a standard 4K block, which is what is generally used with the block storage device. So if the block size of your replication gets smaller, you can start having network degradation performance. So what happens is you have a lot of network overhead with the read and write traffic going back and forth. So if the persistent memory is really replacing your traditional block storage strategy or your replication based on an SSD solution, the latency improvements with the persistent memory can be as much as 10 times. So there's some test cases that we ran where we were actually seeing around 14 times performance improvement on the replication. So in summary, we can have significantly lower replication latency through the Optane DC persistent memory as compared to an SSD or a legacy block storage device. The RDMA with the persistent memory and RPMEM really bypasses the software stack, which reduces your CPU utilization and your network storage overhead. And many of the test cases that we have run, we see we're very heavily using the CPU in a lot of the workloads that we're running. And the more you can reduce the amount that the CPU has to work on with overhead, with tasks such as replication, that expensive resource can be applied to running your workload or giving you better performance on your workload. So RDMA with the RPMEM writes remote data directly to the final persistent memory as really a single hop, which is very efficient. Traditional replication over block storage requires an RDMA move into the DRAM on the remote server, followed by a second operation to move the write data into its final storage location. So the single hop strategy is much quicker. So if persistent memory is being utilized as an SSD replacement, like we did in this case, we can see the typical storage size is usually 4K. That's what we used. You can avoid a lot of inefficiencies seen with small transfers. So really, the key in using this solution is to make sure that you're using 4K or larger block sizes when you're replicating. So, as demonstrated with some of the test data that we have with RPMEM using the persistent memory, we're looking at 10x or even greater performance compared to some of the traditional replication solutions that people are using. So, any questions?
What happens when the block size drops considerably? Let's say down to
So it would just increase the amount of traffic on the network. So we had reasonable performance down to about 256K. And when you get below that level, when you start getting down even lower, it saturates the network. Yeah.
reasonable performance down to 2.6 bytes.
Yeah.
Did you, sorry, go ahead. Did you run any tests comparing Optane to just straight RAM, if you will, and letting it continue to exist at the application level? The responsibility of replication existing at the application level, and then application.
Not at the application level. We hadn't done that. The way we were looking at it was we had to add the read and write times from the block storage device, but we never did it just within the DRAM that I'm aware of. So.
What RDMA adapter did you use for your test? I was very surprised by a sub 2 microsecond RDMA read time.
The physical hardware?
Yeah.
I believe it was a Mellanox NIC. I'm not sure the specific model, so.
100 gig. Picture said 100.
Yeah.
We can find out.
I can find out the hardware.
Well, I just...
Is it sounding too
I may have it in the backup material
Far
here.
too optimistic. Yeah, Microsoft did a little presentation yesterday, and the floor of our RDMA read was north of 10 microseconds, which we were shocked about. We had the same result on 2 names. I've been talking about push mode for 4 years, and it's great to see this number. This number actually shocks me. This is below my expectations.
That's good.
So if it's real, I'm incredibly excited.
Yeah.
We could not duplicate this on Windows with 2 of them.
Yeah.
Definitely talk more about this then, 'cause
Yeah, I can get the actual.
correct numbers.
Yeah, I can get the hardware configurations
Yeah,
back for
we'll
you.
get the details to you.
Yeah.
Are you sure you were doing an RDMA read of non-zero bytes? Let me ask
No, you mean
that.
for the flush, right? Do we use a zero length read, you're asking, or do we do like?
The zero length read does not issue a PCI read. I'm just wondering if maybe you did that.
I'll verify that. That's a great question.
Yeah.
Let me find out, because I know exactly what you're talking about, because we talked about this.
Yeah,
recently.
it validates the handle, but does not issue the PCI operation.
We'll go sanity check that.
Yeah.
Would be very interesting, yeah. I'm pretty sure that we set to non-zero because actually of some advice you gave us
Probably.
a year ago.
Well, that would just be one random question. The
Yeah.
other is, what NIC did you use? Because I want that NIC.
I'm going to sell them on eBay. You can,
Yeah.
As a follow-up to the first question, in a really bad case where the block size gets smaller and you have the most network overhead possible, your lower bound is still better than the NVMe SSD.
Yes. That's a really good point. So.
Getting down to that low tier.
Yeah, we're not going to see 10x, right? It may drop down to 2x or very low, but it's never going to be down to that level.
Because you said it was, quote, really bad, and I'm thinking, well, what is really bad?
Yeah.
It's still going to be not that bad.
Yeah, but you definitely see a degradation coming out. And there's actually a version 2 of the RDMA RPMM replication spec coming out that addresses a lot of the performance issues that we have seen in this first version of the solution. So,
Thank you.
yeah.
I'm surprised that you are using remote replication as an example for showing off the performance, because the RDMA overhead takes off some of the shine.
Okay.
So that is one. Second, related, couldn't one do an RDMA directly to the some NVMe SSD without involving the remote calls CPU? Like peer-to-peer.
Okay.
Kind of thing, and then the SSD has NVRAM within it, so it would not be writing to flash, and it would use its NVRAM for a quick write. So
Right.
it might become comparable to using
Yeah.
Optane DIMM.
Yeah, so one of the things, you bring up a really good point. In this test case where we were replicating, we were actually using the Intel NAND SSD, and it has a much larger cache than the Optane SSD. And it was performing a little bit better, so we used the numbers from the NAND SSD. So the cache plays a big role in the performance of replication. So,
No, my point is you're still engaging the remote CPU
yeah,
to
right. So,
the SSD, and I don't know where peer-to-peer RDMA stands.
yeah.
But is it possible to write?
Yeah, a solution that runs,
There's NVMe over fabrics too,
yeah,
that you can use.
yeah, exactly.
Without engaging
The CPU, and actually you would reduce your latency because you would not have that software penalty.
That's right.
Right.
So then it does not seem like a good example.
That'd be another good data point to put on the charts to see
Yeah,
NVMe over fabrics.
that would actually be an excellent test case that we could run.
Yeah.
So,
Peer-to-peer RDMA is great, but our peer-to-peer PCI transfer via RDMA is great, but it has limited applicability. The byte mode access is much more interesting to a broader class of application. I have a question. If remote replication is a bad workload, which I'm shocked to hear you say that, what's a good workload?
But I'm saying for showing off Optane.
What do you mean for showing it off? It's the ultimate low latency streaming rate workload. How does that?
No,
What's
but
better?
for a local access where you don't have the overhead of RDMA, will show off the difference much more. You know, the difference, and reads will show off.
Oh.
Show it off more.
Well,
for writes can be buffered in NVRAM.
Local access doesn't count because you haven't gotten it out of the error domain. You need to make a copy. That's what replication is all about.
But I'm not saying that it has to be writes.
Yeah.
It could be reads, and I think reads is where.
Okay.
He did have a slide on local. That was the first part of the presentation.
Okay, so reads are great. The last thing you want to do is a PCI peer-to-peer read. You will be a very sorry person once you try to put your workload on that. And PCI reads are horrible. They're slow as a dog. PCI writes are posted. They stream. That's good. PCI reads are not posted. You really don't want to depend your workload on ICG.
Right. PCI is really designed for the DMA agent to be doing the transfer, not a peer-to-peer read and front end.
Right.
That's a good point. They're not, the devices aren't designed for somebody to read the data from you.
Well, they're designed to do it,
Yeah.
but they don't perform anywhere near the same as write.
They're not optimized for that. Yeah.
Peer-to-peer is great for write. Horrible. Horrible.
That's a very important observation.
It's good to know. Yeah. Cool. Yeah, question?
Regarding to the Optane memory, so no information about the endurance is released. And I believe that is much better than the non-touch.
Yes.
First, DRAM.
The endurance is much longer.
And so my question is that, so is there any kind of the background housekeeping operation inside of the persistent memory which may disturb the latency or bandwidth of the access?
Okay, so what was the second part? What was,
Okay, so my question is that is there any kind of the background operation inside of the persistent memory, such as re-labeling or garbage collection,
Yes.
which may disturb the bandwidth?
You know, on a NAND drive, as it has to garbage collect more and more, the latency gets worse and worse.
yeah.
So he's asking, does that happen on these?
Yeah, so there's garbage collection, and you probably are an expert on this one.
Yeah, the simple answer is no. In other words, the latency is the same throughout its lifetime. And it's because there aren't erase blocks and garbage collection tasks like there are with NAND. So, and there's nothing done in the data path, no firmware executed in the data path. And so you get the same performance, whether you consider it good or bad, it's the same throughout the lifetime. And then when the endurance is done.
That said, if you want to really interesting reading, go to the UCSD NBMW page and read some paper by Steve Swanson
Yeah.
that ran the device that Andy has in his hands through performance tests.
Yeah.
It is a very interesting device.
It's very thorough.
It is not as flat as Andy describes.
Yeah.
It is definitely nothing like it.
Could you repeat that citation, please?
So,
You just look up the UCSD and then the product PC persistent memory. You'll find that paper.
yeah.
I think I have a link to it on our website.
So back.
They did an awesome, very thorough job.
very
They found stuff that surprised us.
He had like 2 dozen of his grad students working on it.
Yes.
It's a pretty thorough analysis.
So back to your question on endurance, it lasts much longer than the NAND SSD, and actually Intel guarantees a 5-year plus constant read-write on the product, but the endurance is very long.
We don't have to care about the wear.
Yeah, you don't have to care about the wear.
Lifetime of the server.
Yeah,
Thank you very much.
yeah. And there was a question in the back.
So continuing on that latency question, if lots of writing and cleaning up, the writes and deletes are being done, which would lead to fragmentation. Ultimately, it's a memory, so you will have to do allocations, deletes, and track all those things, and it can lead to fragmentation. And which later on for newer allocations can slow down newer allocations. So will it have impact on the latency?
I don't think you're talking about anything on the DIMM just now. Right? I mean, you're talking about like kernel pools of memory and file fragmentation or something.
No, I'm talking about, latency coming from the lib PMMs which are doing the allocation, which have special allocation calls, right? Memory allocation calls which directly allocate memory from the persistent device.
So again, I don't think you're talking about anything on the DIM. Right? I agree that somebody at some layer has to keep track of which bytes are in use and which bytes are not. And whether it's DRAM or hard disk or SSD, those algorithms can get fragmentation, sure. Right, but the hardware doesn't have any.
Yeah, the hardware, yeah. There was another question in the back.
Yeah. So how much bandwidth do these devices consume? Does each one need 100 gigabit NIC each SSD?
So on the Optane DC persistent memory, so I'll go back to my chart here. So actually, Andy has one in his hand right here. These, the DIMMs actually fit, it's the top left here, these actually fit in the DIMM channels on the board. So a fully propagated board, let's say you have two banks of 6 sockets. You can have, the most you can have would be 6 DRAM and 6 AEP memory. So as you add more memory, you get more bandwidth. So there's no degradation, with the additional modules.
How much network bandwidth do these consume?
How much network bandwidth?
Yes, how much network bandwidth do these consume? Does each one need a 100 gigabit NIC?
So they'll all share the bandwidth that's available on the network. So it's not a dedicated, they will not need a dedicated channel or path.
Go down to the one where you show the read and the write bandwidth. I think that'll answer the question. That one isn't the next one. We have a little table of the actual numbers. There, right
Yeah.
there. So see the thing on the right, that says bandwidth measurement. So of course, a network, your question is really, how much network do you need for how many of these do you have, right?
Yes.
So that gives you an idea right there.
Yeah.
Yeah.
And the 100 gig is probably just make sure the network's not your bottleneck.
Right, you want to remove any bottlenecks. So, I mean, if you had a slow network like 10 megabit, you would definitely have a performance problem. So, yeah. In all of our test cases, we're generally 40 gigabit or faster. So,
Couple of questions, right? One is, how do the AFRs on Optane compare to traditional SSDs, which can be hot swapped? Because Optane memory cannot be hot swapped.
correct.
That's a great question. Yeah.
Can you comment on that?
You.
AFRs?
Yeah, so the failure rate.
Oh, the failure?
Failure rate.
Yeah, they're designed to be just the easy answer without going to lots of detailed numbers is per DIM, the failure rate is designed to be the same as the DRAM DIM. So just ignoring all capacities for a minute, per field replaceable unit, they're designed to essentially be the same failure rate. So about as often as you replace a DRAM DIM is how often you replace
Right.
an Optane DIM. Of course, there are slight variations depending on which SKU and power and stuff, but it's pretty much made that goal. So.
And what has been achieved?
It has been achieved. So far, we haven't seen any data to the contrary. So
Yeah.
we managed to get the same fit rate as an equivalent group in DRAM.
Yeah.
Okay, that's good to hear. That wasn't what I got last time.
Oh, really?
From you guys.
And how long ago was that? I mean, it's just curious.
Less than 6 months.
Because this has always been our site, so
Yeah.
somebody must have.
Yeah,
Yeah.
I mean, I got an answer from other people inside of my organization
Yeah.
interacting with Intel, so maybe there's a
Could be.
communication difference.
That's why we all come to SDC. Yeah.
Actually,
To get the real info.
in all the testing, we have a lot of systems running these right now. I rarely hear of a failure. I only know of one DIM ever being replaced, and that was a early sample DIM that one went out. So.
Yeah, the Cascade Lake rollout in April, Google gave that to.
Yeah.
Yeah, plaque that had a broken Optane killer. Apparently it was because they had put it through a life cycle test.
Yeah, yep, I saw that. That was really good.
I'm gonna slack like that.
Yeah, question.
How much memory is on one of those, or is it variable size, or is it like one size fits all?
Oh, okay, that's a good question. So the DC persistent memory modules come in 128 gig, 256, or 512 gig densities. And again, you normally run these in a pair on a board. So we have a variety of configurations, what we call a 111. You know, depending on what slots you propagate on the board, you can have 2 DRAM and 1 DC persistent memory and only take up half of the slots, all the way up to what we call a 222 configuration, where you can have 6 DRAM, or each socket you can have 6 DRAM and 6 DC persistent memory. You can have a total of up to 6 terabytes on a 2-socket system, Cascade Lake. So now, what people can do with 6 terabytes, that's a lot of memory. So, and then we run in multiple modes. So we can run in what we call memory mode, where you can just plug and play. You run your applications just like you always run them. And what happens is you have a ratio of DRAM to your DC persistent memory, and the DRAM acts as a cache. And we get near DRAM level performance doing that. So you can also run in what we call app direct mode, which everybody's probably familiar with, where the DRAM and the DC persistent memory act separately. You put hot data in the DRAM, and you can write your applications to use the persistence of the DC persistent memory and put colder or move cooler data into that memory. There's different modes that you can run, and then we have a mixed mode or storage over app direct mode, to where you can just partition. You can partition the DC persistent memory into different logical file blocks or block areas, and then you can selectively put information in DRAM or in the DC persistent memory. So it's flexible. There's multiple uses for it. So it does not replace DRAM. You will still have DRAM on the system. Yeah.
So if you know, do you have a ballpark street price for, say, 2 512 gig, if I want to buy a terabyte, 2 512 gig DIMMs, approximately the street price?
So I don't have the specific pricing. I know.
Ballpark figure?
It's on a blog of mine. I put it on a blog of Memory Guy.
Yeah.
It's better to go get that answer than to have non-marketing people.
I'm not a marketing guy. So.
Can you say it?
I don't remember what it is right. But basically what they did was they took the most expensive, 256 gigabyte DRAM DIMM from Samsung, and then said that it would be the same price plus something like 11%. The 512 would be the same price as the 256 DRAM.
Yeah.
So
no.
basically half the price of DRAM.
Yeah, I know when you go to the lower densities, the price per gigabyte is much lower than, like on the 28 versus the 256. So, it varies. The price per gig varies depending on the density of the DIMM. So.
And the OEM, it really varies.
And so
Variability is huge based on how they do their margins. That's why I'm afraid to say a number. But I love it when somebody else says a number.
Actually came off of one of the system configuration slides from the April Cascade Lake.
Yeah.
What's the power differential between comparable size DRAM DIMM versus an Optane DIMM?
So I have the wattage here. It's 12 to 18 watts. So I'm not sure the power levels on the DDR4 DIMM, but correct me if I'm wrong, Andy. The power usage on the DC persistent memory is mostly done when you're doing the reads and writes, but you don't have that constant refresh. So the power signature on this type of memory is much different than the DDR4 DRAM.
Well, I understand I'm a software guy, but I understand that idle power consumption is a benefit.
Yeah.
Obviously, writing is.
This is writing and read is taking the full upwards of 18 watts, which is higher than DDR4 DRAM. I just don't know what it is.
Yeah.
But then you have the idle time where that comes way down. So.
But we're honestly, we're the wrong guys to answer that.
Yeah.
Hardware presentation.
Yeah.
Could you give me some numbers for other modules like 128 gigabyte or 512 gigabyte, especially for light?
It's very close if I recall. I think the 128s were slightly lower bandwidth and 512s are slightly higher. So it's not a significant difference between density on the bandwidth.
As long as you occupy 4 cache lines at the same time, then
Yeah,
you should get the similar number,
yeah,
regardless of the model.
exactly. Yeah.
How about the power?
The power's the same across all the modules.
How about 12 watt case? The number will go below if the power is limited to 12 watt.
By wattage, I don't remember exactly how much it drops down. Again, it's not a significant drop in performance, but it's noticeable. I just don't have that graph with me, so. No, I would have to guess it. I don't know what it is. It's not significant going between 12 and 18 watts, but there is 18 watts is the top performance. So.
The average power consumption would be around 15 watts for max case. Average power consumption in
Yeah, 18 watts is the max case.
max, I know, but how about sustained power consumption?
So it's to sustain. So as long as it's reading and writing, it's going to be at that level. So built into the product itself, if it starts to hit a certain heat threshold, it'll start throttling itself back to prevent damage.
The temperature.
Yeah, exactly. And there is a heat sink on the DIMM.
But you program it to use a certain power level.
Yes, you can. Yeah.
256 byte the sweet spot for reading from this DIMM, in the sense that if you were to read less, we can see that we get
Yeah.
standard. But if you were to read more than 56 bytes, it won't really improve.
It won't really improve. That's the top.
Okay.
So, yeah. So you go all the way up to the 4K blocks and higher and so on. You'll still have that same level of performance. Okay. Any other questions? Okay. Thanks, everyone.